Section 6.6 is solving exponential and logarithmic functions. So with example 1, we'll be solving all four. A is 81 to the third power equals 1/9 raised to the x plus 3 power. So we basically have an exponential equal to an exponential. And what's cool is when you have an exponential set equal to an exponential, it's fairly easy to solve once the bases are the same. So we need to manipulate each of these bases to get them to be exactly the same, which is cool because they could both be written as exponentials with base of 9. So for the 81 to the third power, I'm going to replace 81 with 9 squared. So like not changing the value or anything, just replacing it with 9 squared. And then that's still being raised to the third power. And then the 1/9 raised to the x plus 3, I can also replace 1/9 with like 9 to some power. So since I'm going from, or wanting to go from 9 to 1/9, I'm gonna have to raise 9 to the negative first power. So a 9 to the negative first power will replace 1/9, and then that's still being raised to the x plus 3. And then we need to simplify each side. So on the left, a power to raise to a power, so I'm gonna multiply those exponents. So 2 times 3 is 6. So on the left, I have 9 to the 6th power. And then on the right, another power raised to a power. So multiply them, -1 times all of x plus 3, so think kind of like distributing, becomes 9 raised to the negative x minus 3. So 9 to the 6th power equals 9 raised to the negative x minus 3. And then now think, if I'm saying that like one side of the equal sign is 9 to the 6th power, that means that the other side of the equal sign must be equivalent to 9 to the 6th power. So since they both have a base of 9, to solve for x, we really just have to set the exponents equal to each other. Because if this is 9 to the 6th, then this side is also pretty much going to be 9 to the 6th power, so that they're actually equal. So we'll set the exponents equal. So 6 equals negative x minus 3. And then now I can just solve for x. So I'm going to add the 3 to both sides. And then 6 plus 3 is 9 equals negative x. Divide both sides by a -1, or multiply both sides by a -1. And we end up with x equals -9. And then for b, we have another exponential set equal to an exponential, so 2 raised to the x, or 5x power equals 4 raised to the 2x minus 1. So thankfully 4 is like a power of 2, so we can rewrite 4 as 2 squared. So 2 raised to the 5x power, and then I'm going to replace 4 with 2 squared. So same thing as with a, not changing the value, just kind of changing the base. And then that's still being raised to the 2x minus 1 power. And then we need to simplify the right side. So the 2 to the 5x power stays the same for now. And then on the right, I have a power raised to a power, so I multiply those exponents. Think distributing the 2 by the 2x minus 1. So 2 raised to the 2 times 2x is 4x, and 2 times -1 is -2. And then now I have the same base, and if the left side of the equal sign is like 2 to the 5x power, that must mean that the right side is also equivalent to 2 to the 5x power, because we're saying they're equal. So I can just set 5x equal to 4x minus 2 and solve for x. And then if I want to solve for x, I need to get all my x's on the same side. So I'm going to subtract 4x over. And then 5x minus 4x is just 1x, or just x. 4x minus 4x cancels out, and then we can bring down the -2, or the -2. So x equals -2. So with example C, it's 3 raised to the x power equals 8. So now we don't have an exponential equal to an exponential. The 3 to the x is, but the 8 is just a constant. So our strategies for solving this are a little bit different, because now instead of just getting the same base and setting the exponents equal to each other, we actually have to kind of cancel out the exponential in order to get x isolated. So we know that exponentials and logs are inverses of each other, and then they also kind of like undo or cancel each other out. So if I have an exponential with a base of 3, but I want to get rid of it and just be left with x, I have to log base 3 both sides of the equation. So I'm going to log base 3 the left side, and you're literally kind of like as if we were subtracting 4x from both sides. Like it's just an operation that we're doing to both sides. I'm going to log base 3 both sides, so the left side becomes log base 3 of 3x, or 3 to the x power, and then the right side becomes log base 3 of 8. And then now the log base 3 and the exponential with a base of 3, those are inverses, so they cancel each other out. And we're just left with x equals log base 3 of 8. And then if we want to get a decimal approximation of it, we can use the change of base formula. So with the change of base formula, it would change into x equals, and then log base like 10, so just log of 8 or common log over log of 3. And the reason that we use the change of base formula is because as it's written right here, this can't be evaluated in a scientific calculator because scientific calculators just use common log and natural log, so log with base 10 or log with base of e. But if we use the change of base formula, we can change it into common log, and then now we can evaluate this in the calculator. So log of 8 divided by log of 3. So it's approximately 1.893. And then with D, 4e raised to the negative 0.3x minus 7 equals 13. So we just have one exponential again like we did on this side. Eventually we'll have to log both sides in order to cancel out the exponential, but before we do that, we really need to kind of isolate the exponential. So you would use the same like kind of like steps you would use to solve like a regular equation where you're trying to isolate the variable. So I'm going to undo this like minus 7 by adding 7 to both sides. And then I'll bring down the 4e raised to the negative 0.3x. Negative 7 plus 7 cancels out. 13 plus 7 is 20. And then now the 4 is not a part of the base. The e is the base of the exponential, so I can still cancel out this 4 by dividing both sides by 4. And then 4 divided by 4 cancels out. I'm just left with e raised to the negative 0.3x of 20 divided by 5, of 20 divided by 4, so of 5. And then now I have e raised to, or exponential with the base of e, and it's raised to the negative 0.3x. So if I want to like basically get rid of the exponential or cancel out this e, I'm gonna have to log both sides. But since the base of the exponential is e, I'm going to use a natural log on both sides because a natural log is a log with a base of e. So ln, or natural log of e raised to the negative 0.3x, and then equals natural log of 5, because this natural log will cancel out the exponential with the base of e because they're inverses. So they cancel each other out. I'm just going to be left with negative 0.3x equals natural log of 5. Then if I want to get x by itself, I need to divide both sides by negative 0.3. And then finally I can go ahead and I can divide natural log of 5 divided by negative 0.3. So for ln, still in the upper left hand corner, but ln, or natural log of 5 divided by negative 0.3. So about negative 5.365. So just to kind of recap that section, when you're solving an exponential or when you're solving equations that have exponentials and both sides of the equal sign have exponentials, then you'll just need to get the same base and but you'll get the same base and then set the exponents equal to each other. For C and D, when we had just an exponential on one side of the equal sign, you want to isolate the exponential and then log both sides in order to cancel it out. For example 2, your sister is cooking her famous chili. When she takes it off the stove, the temperature is 212 degrees Fahrenheit. The room temperature is 75 degrees Fahrenheit, and the cooling rate of chili is R equals 0.051. How long will it take to cool the chili to a serving temperature of 95 degrees? So we'll use the equation for Newton's law of cooling. T equals T sub 0 minus T sub R times E raised to the negative RT plus T sub R. So T sub 0, that stands for the initial temperature. So in this case, the initial temperature of the chili. So T sub 0 it starts off at 212 degrees Fahrenheit. And then T sub R, that's the room temperature. So the room temperature is 75 degrees Fahrenheit. And then the T that we're looking for is, or the T that we're solving for is like the temperature that we want. So we want the chili to get to 95 degrees Fahrenheit. So T without like the sub or anything is just 95 degrees Fahrenheit. And then the cooling rate is that R equals 0.051. So we can begin just by plugging everything in, and then we'll start to simplify. So T equals is 95 equals, in parentheses, T sub 0 minus T sub R. So 212 minus 75, and then times E raised to the negative negative RT, so negative 0.051 times T. Because we're trying to find the time, so we're solving for T here. And then plus T sub R, so plus that 75 degrees, the room temperature. And then now we can start simplifying. We'd simplify the inside of the parentheses first. So 95 equals 212 minus 75 is 137. Times E raised to negative 0.051 T, and then plus 75. So now if we start to look at this equation, we can see that we have one exponential. So I know that eventually my goal is going to be to log both sides in order to cancel out the exponential. But before I do that, I need to isolate the exponential. So I'm trying to isolate just the E raised to the negative 0.051 T. So I can cancel out this plus 75. I can subtract 75 from both sides. And then 95 minus 75 is 20 equals 137 E raised to the negative 0.051 T. And again, we're solving for T. So eventually I'm gonna have to find a way to get rid of this exponential and get this T freed, for lack of better terms. But before I do that, I can keep isolating the exponential. I can cancel out this 137 because the E is the base. The 137 is just being multiplied by it. So I can cancel that out by dividing both sides by 137. And then 20 divided by 137 is about 0.146. And then equals the 137 divided by 137 cancels out. E raised to the negative 0.051 T. So now our exponential is isolated. So I can go ahead and log both sides in order to cancel it out and get this out of the exponent. So because my exponential has a base of E, I need to natural log both sides. So natural log of 0.146 because a natural log is just a log with the base of e, and we need the base of the log to match the base of the exponential. And then ln of e raised to the negative 0.51t. So I'm going to rewrite this up here. I'm just going to leave this as natural log of 0.146. And then on the right side, the natural log and the exponential with the base of e undo each other. So we're just left with, I left a 0 off here accidentally, but we're just left with negative 0.051t. So now we're close to having t isolated. So in order to isolate it fully, I just have to cancel out this negative 0.051t by dividing both sides by that value. So divide both sides by negative 0.051, natural log of 0.146 divided by negative 0.051 is about 37.73. These cancel out, so we're left with t is approximately 37.73, and this is in terms of minutes, so about 37.73 minutes. So on to example 3, more solving. So you'll see now instead of solving exponentials, we're going to be solving equations that have logarithms. So if we look at 3a, natural log of 5x plus 2 equals natural log of x plus 10. So just like when with equations that had exponentials with the same base on each side, we could set the exponents equal to each other. You can kind of do the same thing with logs because logs are just exponents. So if I have the same type of log on both sides, natural log of 5x plus 2 and natural log of x plus 10, I can just set these equal to each other. So 5x plus 2 equals x plus 10. And then now if I want to solve for x, I want to get my x's on both sides, or on the same side of the equal sign. So I'm going to subtract x from both sides in order to cancel out this x. 5x minus x is 4x, plus 2 equals, bring down the 10. And then now to solve for x, I can subtract 2 from both sides, bring down the 4x. 4x equals 10 minus 2, so 8. And then divide both sides by 4, and you end up with x equals 2 as your solution. And then for b, log base 6 of 6x equals log base 6 of plus log base 6 of x minus 1 equals 2. So now we can start to think about like using properties in order to simplify the left side of the equation, because we know like there's a product property that occurs like either when we're multiplying two values together or we're like adding two separate logs together. So these have the same base, so I can rewrite them using the product property by multiplying the 6x and then x minus 1. So I can condense them into log base 6 of 6x times x minus 1. And then equals 2. And then now I can simplify the 6x times x minus 1 just by distributing. So log base 6 of 6x times x is 6x squared, and 6x times negative 1 is negative 6x. And then equals 2. And then now I have a log on just one side. So it's not like a where we can just set each of these equal to each other because I don't have a log over here. So if I have a log on one side that I need to cancel out to get x out, I'm gonna have to exponentiate each side. So that means basically apply an exponential to each side of the equation. Since this is a log with a base of 6, I'm gonna exponentiate by 6. So I'm gonna take each side of the equation and make it basically the exponent of an exponential. So it's going to be 6 raised to the log base 6 of 6x squared minus 6x. and then equals 6 raised to the 2 power. So everything in this line just became an exponential. That's what it means to exponentiate. And then the exponential with the base of 6 and the log with the base of 6, those are inverses of each other. So they cancel each other out. And we're just left with 6x squared minus 6x and then equals 6 squared, so 36. And now I have a quadratic, I just need to get it in standard form to solve. So I'm going to subtract the 36 over, and then I end up with 6x squared minus 6x minus 36 equals 0. I can divide a 6 out of this entire equation. I'll see if I can just squeeze a little note in there about it. So I'm going to divide the entire equation by 6 because each term is divisible by 6. So the 6x squared becomes x squared minus x minus 6. And then I'm looking to factor it, so I just need factors of -6 that add up to -1. So it would be -3 and +2. So factors into x minus 3 times x plus 2 equals 0. Now I can set each factor equal to 0 and solve for x. So when I do that, I end up with x equals +3 when I add the 3 over, and -2. And we just want to check to make sure that each of those answers make sense and they're not creating like a domain restriction, because we know with logs there's going to be a domain restriction, and basically we can't be like taking logs of negative numbers. So if I plug in 3 for x, this is log base 6 of 18, that's okay because it's positive. This is log base 6 of x minus 1, so 3 minus 1, so 2, so that's positive, that's okay. If I plug in -2 though, then it's log base 6 of 6 times -2, so log base 6 of -12. And you could stop there, because if you think about it, like, you can't raise 6 to a power and get a negative number. So -2 is not within the domain, so it's extraneous. So x equals 3. And then for C, log base 3 of 10x minus 9 equals 4. So we have just a log only on the left side. So to cancel it out, I'm going to have to exponentiate both sides. So this is a log base 3, so I'm going to exponentiate both sides of the equation by 3. So 3 raised to the log base 3 of 10x minus 9 equals 3 raised to the 4th power. So everything in this line just becomes an exponent here. And then the exponential with the base of 3 and the log with the base of 3 undo each other. So I'm just left with 10x minus 9 equals 3 minus 4, so 81. Or sorry, 3 to the 4th power, not 3 minus 4, but 3 to the 4th power, so 81. And then if I want to solve for x, I need to cancel out this minus 9. I'm going to add 9 to both sides. I can bring down the 10x. These cancel out. 81 plus 9 is 90. And then if I divide both sides by 10 to isolate x, I get x equals 9. And then just to check in your head, if I substitute an x equals 9 here, 10 times 9 is 9, and then minus 9 is still a positive number, is 81. So x equals 9 is fine, it's not extraneous. And then for D, log of 5x plus log of x minus 1 equals 2. So both common log, both have the same base. So that means that we can condense this using the product property. So I can condense it into log of 5x times x minus 1 equals 2. And the reason we have to condense it like for B and for D is because we can't really exponentiate each side when there's multiple logs, when there's multiple terms there, because it doesn't cancel out in the same way. So we have to condense it if we're able to. And then now I can simplify the inside here. So log of 5x times x is 5x squared. 5x times -1 is -5x, and then equals 2. So now I have the left side simplified, meaning I've condensed the logs, so I'm able to exponentiate. We want to have just one term really on each side before we exponentiate each side. So this is a common log that has a base of 10, so I need to exponentiate each side by 10. So 10 raised to the log of 5x squared minus 5x, and then equals 10 raised to the second power. So this line just becomes the exponents of this line. And then exponential with base of base of 10, it cancels out a log with a base of 10. So these undo each other. I'm just left with 5x squared minus 5x equals 10 squared, so 100. And then now I have a quadratic, so I can isolate, I can get it in the standard form and try to factor it. So I'm going to subtract the 100 over. I get 5x squared minus 5x minus 100 equals 0. They're all divisible by 5, so I'm going to divide out of 5 to make it easier to factor. And then when I do that, 5x squared divided by 5 is x squared. Negative 5x divided by 5 is negative x. Negative 100 divided by 5 is negative 20 equals 0. And then now I just need factors of negative 20 that add up to negative 1. So that's negative 5 and 4. So factors into x minus 5 times x plus 4 equals 0. And then if I set each factor equal to 0 and isolate x, I end up with x equals 5 and negative 4. And then just to check for extraneous ones, if I plug in positive 5, I get log of 25, and log of x minus 5 is log of 4. Both like taking the log of a positive number, so that's fine. There's no like domain restriction on positive numbers. And then for x equals negative 4, if I plug in x equals negative 4 here, the log of negative 20. So you can't take the log of a negative number. So that means that negative 4 is extraneous. So it doesn't mean that necessarily all negative x values are extraneous. It just means if you plug it in and you end up taking the log of a negative number, it becomes extraneous. For section 6.7, it's modeling with exponential and logarithmic functions. So for this section, we're just going to go over one type of problem. There's just two examples from that one type of problem. So example 1, write an exponential function y equals ab raised to the x power whose graph passes through 110 and 340. So we're going to create an exponential equation based on both points and then use those two equations to, it pretty much creates a system. So we'll be able to solve for x and y. So equation 1 is going to be in the form y equals ab to the x, but we'll plug in this first point, so 1 for x and 10 for y. So instead of y equals, it's 10 equals ab to the x power, so ab to the first power. And then we'll create a second equation for the second point. So equation 2, same format, but 3 will go in for x and 40 will go in for y. So instead of y equals, it's 40 equals still ab to the x. So ab cubed. And then now we've created a system. So we have two equations with two variables, so we can solve it like a system of equations. And you can use like technically elimination or substitution, but elimination is like a little bit different because we're not adding the equations together. Sometimes you can divide the equations by each other in order to like solve for a and b. So these ones I'm just going to show substitution. If you want to experiment with like dividing each equation, like for example, I could divide out to cancel out the a. That's on you. You can try it. It works fine. So I'm going to solve this first equation for a, and then we'll substitute it into the other equation where a is. So if I solve this first equation for a, that means I have to divide both sides by b. So b to the first power, just b, those cancel out. And I'm left with a equals 10 divided by b. So now that can get substituted into the second equation where a is. So the second equation becomes 40 equals, instead of a, 10 over b. and then times b cubed. And then now to simplify and solve for b, I know like b and b cubed, at least one of the b's cancels out. So if I use this b to cancel out one of the three b's up here, I'm left with 40 equals 10 times b squared because one of the b's from the b cubed cancels out. And then if we want to solve for b, we have to isolate it. So we're going to have to cancel out multiplying by 10 by dividing both sides by 10. And then 40 divided by 10 is 4 equals, these cancel out, b squared. And then we can square root both sides in order to get b completely by itself. With these, we don't have to worry about the positive and negative answer because b is my base and I can't have a negative base of an exponential. So I end up with b equals 2. And then I can take that b equals 2 and I can substitute it into this equation to figure out what a is. So this b equals 2 will get plugged in here to solve for a. So a equals, instead of 10 divided by b, it's 10 divided by 2. And then we end up with a equals 5. So we have a and we have b now. And we can write our exponential equation in the form y equals ab to the x power. So y equals, a was 5, so 5 times b was 2, so 5 times 2 raised to the x. And we can't simplify this further, like the 2 needs to stay in parentheses because the 2 is the base of the exponential. The 5 is just the coefficient, or kind of like a stretch. And then for the next example, write an exponential function y equals ab to the x whose graph passes through 212 and 324. So we're going to create two equations again. So for the first equation, 2 goes in for x and 12 goes in for y. So y equals becomes 12 equals ab to the x becomes ab squared. And then for equation 2, 3 goes in for x, 24 goes in for y. So 24 equals ab cubed. So same thing, we've created a system of equations now. Like I said, you can technically like divide and solve for b that way. So I'll show you with this one because it cancels out even more so than the other one. If we want to go the division route, you don't have to, you can always choose between these two strategies. If you want, you should probably take the like equation that has the higher power of b and then divide the one that has the lower power of b. So I can take 24 equals ab cubed, and I can divide that by this equation, 12 equals ab squared. And then 24 divided by 12, we're just like dividing vertically pretty much. 24 divided by 12 is 2. A divided by a cancels out. And then b cubed divided by b squared. Like this b squared cancels out 2 out of the 3 b's up here. So we're just left with b to the first power. So b equals 2. And then now that we know what b is, we can figure out what a is. We don't really have like one of these like good, nice equations to plug b into to figure out a because we didn't use substitution. So we can just go into either one of the original equations. Probably the first one is easier because it has a lower power of b. So for the first equation, it was 12 equals ab squared. So a times 2 squared. And then just make sure you follow order of operations. So we'll simplify exponent first. So 12 equals a times 2 squared is 4. And then to get a by itself, we can just divide both sides by 4. These cancel out, and then we're left with a equals 12 divided by 4, so 3. So a equals 3, b equals 2. Once we have a and b, you can write your equation. So y equals ab to the x. A was 3. And then b was 2, so 3 times 2 in parentheses to the x power. Same thing here, we can't like we can't multiply the 3 and the 2 together because just the 2 is the base of the exponential.